You increasingly need to become learners who act and thereby receive additional light and knowledge by the power of the Holy Ghost, and not merely passive students who are primarily acted upon. Okay, this idea, right, of active or passive, right? Are things happening to you, or are you deliberately taking steps to make sure you have the Spirit in your life every day? That's really what the question is, and that's a very important concept. Okay, thank you very much. All right, let's see if the camera will work on this one. Okay. All right. So I sent you all an email trying to make sure everybody heard the same information. It was kind of long, which I know are sometimes hard to digest. Do you have any questions about the plan? It's next week. Yes. Okay. Elena's got the sheet over here on this side. They need some. So raise your hand if you still need 2 pages of the sheet. Okay. Raise just one finger if you just need 1 page. Raise your whole hand if you need both. So you got one right there. Elena. Thank you. Okay. All right. Questions about the things that were in the email? About looking at exams, about what the finals could be like, about the dosimeter project. It's all crystal clear. No questions.
For the dosimeter project, you have to choose 8 consecutive hours.
The ideal would be 8 consecutive hours, like representing a work day. But if you did 4 hours one day and 4 hours the next day, or 2 6, or it's okay, but you need at least 8 hours and on your graph, annotating when things happen, right? So you can make your graph in Excel, right? There are directions for that under content assignments. And then if you want, you can screen capture that and like put it in PowerPoint and then put your annotations in there. And then if you group it all and right click it, you can export it as a figure, like a JPEG. So then you can put in your figure. Yes.
Do we have to make the graph that exactly?
You may make the graph however you would like, but it needs to show the data and some arrows showing what you were doing at certain times.
So the graph is just like one line showing the 8 hours of data and then annotating your events online.
Exactly. Mhm. Yes.
So on mine, when I it likes to make the graphs a little at 8 hours for each off time.
Oh, then, yeah, 5 minutes will not be no, so it's okay. Yeah, no, if it's, yeah, we'll say 8 hours plus or minus 5 minutes. It's all right. Yeah, no, that's okay. All right, good. Other questions about the dosimeter project, the paper, looking at tests during lab times, rules? What the finals gonna be like? Yes, please. The final is cumulative over all 3 units.
No, it's over the testing center for the entire.
Sorry. The final exam is available in the testing center for the entire final exam period. Yes. That is true. There are 2 pages to the handout. Okay, other questions about finals? Okay, so today and next time, we're going to be trying to pull all of these ideas together. And in particular, let me see if I can find it real quickly. All right, trying again. Syllabus. Okay. So these are your learning outcomes. This is what we're trying to figure out if you know how to do. Okay. Define the basic terminologies of acoustics, identify physical principles in common situations, answer conceptual questions related to hearing, speech, audio, listening environments, and musical instruments. And then apply scientific models to analysis of hearing, speech, musical instruments, etc. And then solve basic problems relating to hearing, speech, audio, listening environments, and musical instruments. And then write effectively using the terminology of acoustics and logically outline how acoustics is important in the discipline of your choice. Okay, so those are the main things. And then there's also the GE learning outcomes, specifically for our science class. Develop a heightened interest in the physical universe, improve your ability to understand, explain, and predict natural phenomena, Explain the process of the scientific discovery, how others have used it, its strengths and limitations. Explore the whys and hows, the questions of science, as well as the what's, the facts, so that science is seen as a legitimate avenue of seeking truth. So that's what this course was designed to try to help you do, was to gain these learning outcomes, okay? And I know that for some of you, the music unit especially was like, whoa, this is so much and I'm never going to use this again type thing. But it really was all about this idea of applying our models, right? In all of science, we develop these simple models based on things that we know the answer to. And then we apply it to the physical system and we see how much of that physical system can be explained by that. And then we figure out what's the next thing we can add to our model to make it a little better. I was thinking this weekend that that's kind of, you can think of that as a way that we also strive to become disciples of Jesus Christ. Right? What is the basic model for a disciple of Jesus Christ? The fundamental, the underlying, captures a lot of what's important about being a disciple of Jesus Christ. Love one another, right? That is the foundation. Like, you're not going to get anywhere, right, if you don't have that basic thing. And you can go a long way towards being a disciple of Christ by following that command of the Lord, right? But as that only takes you so far, actually, right? There are some extra things we have to do to truly be disciples of Jesus Christ. He says, if you love me, keep my commandments, right? He says, you know, he provides us ways to make covenants with him and to make these promises. And those are all these extra things that help us become more and more like what his and Heavenly Father's reality is, right? So we're looking at it from our limited earthly experience, right? We don't know necessarily why covenants, why baptism is a key to the gate. Like, we don't understand like really why, right? Like, why every time the Lord, Heavenly Father, announces Jesus Christ is one of the first teachings about baptism. We don't really know why that is so key, right? But the Lord has told us that in addition to the base model of love one another, that these are the things that will get us closer and closer and closer to him. Okay. So it's just really interesting to think about that progression, right? And how that hierarchy kind of comes into play. And if you don't have that base model, right, you can go trying to add different things in, but you're going to miss the whole foundation principle. Right? So I think that's kind of an interesting way to think about this idea of models. And it's used all over in science, in every field. All right. Any other thoughts or questions about that? Okay. All right. So let me explain now this sheet. Okay. This is my attempt to help you review everything you have learned in a way that ties things together instead of having them be separate. Okay. So natural frequency is the first slide. Okay. And under that is pitch, period of oscillation, and resonance. Okay. So then to tell you which items we've discussed that have to do with those topics, the Roman numerals are the unit review sheet, and the Q is the number on that unit review sheet. Okay, so the 2-Q5, Q7 means that on review sheet 2, questions 5 and 7 and 8 and 31, sorry, there's a lot on 2, all have to do with pitch. Does that make sense? So if you're wondering, okay, what about this idea? Where do we learn about this idea? That kind of helps you figure out where on the review sheets to find applications of that concept. Questions about that? I have to read my shorthand here. All right. So we'll just start at the top. We'll get probably hopefully through the first 2 pages today, or at least the first 5 or so of these little boxes, and then we'll do the rest next time. And Emily, can you bring your accordion next time? Okay, we'll have the accordion and we'll have another demonstration next time. We have one for now for when we need to relax our brains in about 20 minutes. Okay, all right, so natural frequency, the ideas of pitch, the periodicity of the oscillation, and resonance. What do you want to know about that? What questions do you have about those things? Or when we use them, or how to calculate things. Oh, real quick, while you're pondering that, your final exam is gigantic. Okay. It is less than half of it are the actual 80 questions. Okay, because basically all the stuff that was on the back of your other 3 tests are all on this test too. Okay, so I asked the person in the office to staple them separately and then staple them together. Okay, so you could undo one of the staples and look at them as 2 pieces. And then have it stapled back together when you release the testing. Okay, because I know it's very hard to keep track of what question you're on and flip through all of those. Any questions about that? Anybody want me to say that a different way? Yes, okay. So there are the 80 questions, and there's all of the supplemental materials, the graphs, the equations, you know, the tables, all of that. Because it's hard to be thinking about your question and flipping through the pages. The questions and those reference materials are stapled separately and then stapled together. So if you are careful, you can figure out which staple is holding them together and undo that while you take the test. And then when you hand it back in, just have them restaple it together. Okay, so hopefully that will make it a little less frustrating to flip through 30 pages or whatever it turned out to be. Okay. Any other questions about that? Yeah. Yes, all the resources of the previous exams will be there. All the equations, tables, graphs. Yeah, exactly. So if you, on the web page, on the Learning Suite web page, just on those exam preparation materials, those, all 3 of those sections will be there. Okay, good. Yes.
If we go, like, if we go over the steps and go over questions on the file, like, should we do that?
Yeah, so the best way to prepare is to go over your 3 review sheets, right? Of those 120 questions or topics, about 70 to 75 are on your final. The other 5 to 10, I don't think it's all the way to 10, but I think it's more than 5, are, can you pull the things together? Can you say that, yes, this, and this are all examples of reflection? Even though we talked about them in different places, right? Does that make sense? And then, you know, can you, just a few that are like, can you take these principles and go the next step? But it's not even 10% of the test, I don't think. Somewhere in that 5 to 10% of the exam questions are actually, can you pull these things together? Okay. All right, good. Other questions? It is a big test. It is hard simply because you have learned so much, right? There's just a lot of material, but the level of the questions is not harder than they were before. Okay. Right. Yes, please.
Also, it says those on natural modes page.
Yes.
Under resonance, what is that?
So that is referring to the bottom of page 3, where it says natural mode. All of those natural mode things are manifestations of resonance. Okay, good question. Other questions about that? First section on natural frequency. That would be the pitch period of the oscillation and how that relates to frequency or resonance. Okay, so then there's the mass string model, mass spring model that we talked about. Okay, so if we remember that, this is one of our basic models. We have some mass, we have a spring with some stiffness. And then we have the frequency. There's a 2 pi out here, but we won't really worry about that. The square root of the stiffness over the mass. We're never using this to calculate, just to show the relationship, right? When will the natural frequency increase and when will it decrease? Okay. All right. So on the little slide there are some of the interesting ways that we've applied this mass spring model to realistic systems. Okay. So basilar membrane. How did the mass spring model relate to the basilar membrane? Remember? how that was? What did the mass spring model teach us about how the basilar membrane? I'd rather not be the only one talking today. Joe. The resonances, right? So the basilar membrane, as it goes along, has different resonance or natural frequencies because of the variable stiffness and mass or density. Density is the mass per unit length in this case. Good. How about the vocal folds? How did we use the mass spring model on this idea of vocal folds?
Sorry, back to
Oh,
basilar
sure.
membranes. Was the mass and the stiffness of the basilar membrane itself? So
Yes.
like different sections were different stiffnesses, meaning it resonated at different frequencies.
Exactly. The physical properties of the basilar membrane change as you go from the oval window to the helicotrema, such that the resonance of the frequency of the basilar membrane changes from very high, the highest we can hear next to the oval window, and then the lowest we can hear at that relatively not stiff, relatively massive end by the that's free to move. Okay. Other questions about that? Okay. All right. So then we have the vocal folds. Yes,
Was it like tension and frequency?
exactly. So that tension of the vocal folds, right? As the tension or the stiffness increased, what happened to the resonance frequency? It goes up. And because they're stretching, they're also effectively less dense. And so that part is going down. So both of those give you a higher fundamental resonance frequency or frequency of motion of the, frequency of motion of the vocal folds. Helmholtz resonators. Everybody remember the Helmholtz resonator? This is one of the extra credits you can do too, is what was a lab, but we didn't do it as a lab this year, right? Of the idea of, I just have to drink my water first. Use these. Okay, I don't think we showed these, right? These are glass tubes that have heating elements at the bottom. Okay, and as these heating elements, they're going to disturb the air, right? Because what happens to hot air? It rises, right? So this hot air is going to rise, and then it's going to reach the end of the tube and have a different flow condition, right? So a reflection is going to happen. And then some of that will be reflecting back in, some of that pulsating air will reflect back in and back up, okay? So eventually, this will sing for us. Okay. All right. But with Helmholtz resonators, it's really the idea of like your water bottles, blowing on your water bottles, and how that can be related to, I guess I can just dump water out since I have a sink right here. Right. That's related to the stiffness. The stiffness is analogous to the volume of water here, and then the air here, and then the mass is analogous to the neck, the air in the neck. Okay, so I have my two tubes, right? The frequency that they're at. Let's see. I think only this one is singing right now. Here, right? How does that make it longer, soft, shorter? Okay. And then as soon as, if this one will start to sing, what should we hear? Can you see? Sorry. If they're slightly different frequencies, what should we hear? Or lengths, what should we hear? We should hear beating. So that'll tell us if the other one's heater is working well enough to actually do anything. Is it too annoying to leave it on for a minute? It won't leave it on. Okay, good. All right, and then another thing we used the mass spring model for was this body resonances of instruments, particularly our string instruments, and even things like soundboards, right? So what was the, what does it tell us like about the air and wood resonances of a string instrument? How is that related to this mass spring system? Yeah.
Just like the whole phone, besides the tension goes up, like
Yeah, so if the tension in the wood or the stiffness of the wood goes up, then those resonances associated with the wood resonances will go up. just like in this mass spring system, right? And if you have a larger volume or mass of air, then the resonance of the air resonances will go down. Any questions about that? Yes, please. Oh, yeah, so you turn, if it was an empty bottle, you turn it upside down. The spring is the air here in the body, and then the mass is the air in the neck. Okay. I think that other one is not heating well enough. We definitely should do that. But that is an example of our other model. On the next slide, this string and tube models, right? We have, are you guys tired of hearing this yet? Fixed strings, open tubes, open closed tubes, right? We've applied it in an amazing number of ways, haven't we? This basic model gets us a long way towards understanding a lot of the acoustics. Okay, so what questions do you have about it? These are some of the few equations that you need to memorize in our class, right? The F1 is V over 2L, or F1 is V over 4L. And then whether they have all of the harmonics, all the multiples of the fundamental, or only the odd multiples. Okay, so look at that list and see if there are any of those you would like to. Yes, please.
Can we go over Singer's formant and formant tuning?
Yes,
Concepts?
let's do that. Okay, all right. Okay, so under the open closed tube section, another one that could be there, right, would be the ear canal. The idea that the ear canal is open at the pinna and closed at the eardrum, right? Which that length right there tends to give us, when you do F is V over 4L for its resonance frequency of our ear canal. Typically, it gives us something around 2000 hertz. Depending on the length of your eardrum. Okay, so then in the Singer's formant, okay, which is used by tenors to be heard above the orchestra. Say to project better, okay, to have higher energy. Okay, the idea is, so you have vocal folds here, and then you have the vocal tract, right? You can make it all sorts of different shapes. In the Singer's formant, the idea is that they drop their vocal folds, their larynx, their voice box, just a teeny bit. Okay, so they create an additional little tube here that changes the formants of the vocal tract. And it basically changes, typically it's F2 and F3 for most of the vowel sounds, to create a large vocal tract resonance or for new formants. In the 2 to 4 kilohertz range. I can't remember the exact numbers. Up in that range, which is particularly easy for our ears to hear. So that's the Singer formant idea. Now with formant tuning, that is less related to, well, it's related to the open closed tube idea only because the vocal folds represent the closed end and the mouth represents the open end. But we're not using the F equals V over 4L equation because it's typically much more complicated than that, right? But in formant tuning, the idea is that the sopranos change the vocal tract, they change the vowel that is being sung. To align those vocal tract resonances or formants with the note they want to sing. Yes, please.
Can you remind me why it's just sopranos?
Because the idea is that it's harder to sing well and loud and on pitch at higher frequencies, right? And so they basically have learned how to modify the vocal tract to make that easier, to get higher vocal power or efficiency by slight modifications to the vocal tract that sacrifice the exact like intelligibility of the word for the sound power. So I got to go see a very fun, brand new opera written by a BYU graduate student on Friday night. So that was very, very cool. It's called He Shall Prepare the Way. You can find the music on Spotify. It was an interesting retelling of the story of Lehi's family leaving Jerusalem. And one of my favorite parts, other than the music was spectacular, was the fact that he doesn't really paint Laman and Lemuel as villains. Well, he didn't at all. He just painted them as perfectly normal people who were asked to do a really, really hard thing. And how sometimes we react to that. So it was very beautiful. Okay. All right. Good. Any other questions on that string and tube modes? Yes, please.
Can we go over the effective length of a wind instrument once more?
Yes. Okay. All right, so for most of our wind instruments, the fundamental frequency is tied to the length by V over 2L, except for the clarinet, which is V over 4L. Clarinet then will have just the odd harmonics, right? Whereas this one would have all the harmonics. Okay. All right, so the length is in the bottom, right, in both cases, right? So the frequency or the natural frequency, the pitch, the fundamental frequency is inversely related, meaning if one goes up, the other one goes down to the length. So anything that increases the length will make the pitch or the fundamental frequency go down. So in a trombone, when they move the slide out and make the tubing longer, that would decrease your pitch, right? On the wind instruments that have keys, the more keys you close, then more tubing for the air to go through. Okay. And then just the one other thing is that idea of end corrections, with the key idea there being that wider tubes have larger end corrections.
For this one answer, like the term number 3, do you have to memorize the end correction?
You don't have to know the formula. You don't have to know the exact numbers, just the concept of effective length and how that changes. Yes.
Are there any other instruments that have the odd harmonics?
There are not. The saxophone and the brass, all of the rest of the reed instruments and all the brass instruments or lip reed instruments, they all are really closed open. But none of them are as cylindrical as the clarinet. All the rest are cone-shaped or conical, which means that this relationship we've done right here, right? So these, this relationship here is only for cylindrical open closed. And the math is then different if you have a cone instead of a cylinder. And the physics is different if you have a cone instead of a cylinder. And what it does is it changes the relationship so that it becomes more like our open model with the V over 2L and all the harmonics. But it is the conical shape, and then with the brass instruments, the addition of the bell that do those things.
So you have the F1 equals V over 4L and then F2 is 3F1. For the all harmonics, is that 2F1
Yes.
equals F2?
Yeah, F2 would be 2F1 and F3 would be 3F1. So the bell does a lot of things. Anyway, in the slides for that unit, there's a list of all the things the bell does. There's about 8 of them. But one of the things the bell does is take the brass instruments from being just odd harmonics to all harmonics.
So like a trombone is open closed, but you wouldn't use E over 4L?
Exactly.
Okay.
So for the trombone, for the brass instruments, it is open closed because the lips are like the vocal fold, they're like a closed end, the bell is open. But this model doesn't fit because it's not a pure cylinder like the
Okay.
clarinet. Mhm. Other questions? Okay, moving on to page 2 then. Haven't thought about most of this in these next 3 slides for a while. We'll be talking about them, but not specifically. It's been a long time since you first learned about them. Okay, so this is then the wave properties. Okay, transverse versus longitudinal. Questions about how you would identify if a wave is a transverse wave or longitudinal wave. Driven or free? How are we doing on that? Be brave. Yes.
Can you just go over how like plucked and like struck strings are driven or free, like?
Yep. Let's do it. Okay, so driven means that energy is supplied over a long time. Like more than an instant, right? For some amount of time. Where free means the energy is delivered in an instant, right? It's just impulsive. So anything that is plucked or struck will be free. Right. Anything that is bowed or blown is driven.
Press the piano key and hold it down. Is that the example of driven or free?
So if you press a piano key and hold it down, that is still a free oscillation because the striking only happens once. If sometimes people use the piano more as like a different kind of instrument and they bow the strings, then you would be driving the string. But if it's ever struck, it's free.
However, the organ is driven.
The
right?
organ
As
is
soon as you
driven.
Lift off.
Yes, because that as long as the key is compressed, air is flowing, adding energy. And as soon as you lift the key, the air stops. Very good.
Is doing a roll on a drum as a driving instrument kind of like you do bone instruments? It's like a stick slip thing, so it's like a bunch of like hits at once that drag.
It's a bunch of impulsive strikes, and to get a good snare drum sound, the bouncing of the sticks has to cooperate with the bouncing of the membrane.
Yeah, but is it
So-
driven at that point? Is it driven?
You could think of it that way. We won't worry about it for the class generally, but yes, that would be an example of like pushing a swing, right? Because if you're delivering energy every time the membrane bounces to a certain point, that would be like driving a string or pushing a swing, I mean. Right, because every time it comes back, you push it. So, yeah. That's good, good question. Okay. Yes, please.
Could you quickly describe transverse and longitudinal?
Yep. So transverse waves, the displacement, the motion, okay, of the medium, the string or the air or the surface is perpendicular to, okay, the motion of the wave. So our biggest example of this for our class is strings, right? Because each piece of the string is just moving up and down, right? As it goes from one to another, okay? But the wave itself is moving to the side, left or right. Whereas in longitudinal, the displacement of the medium is parallel to, oh goodness, longitude. Okay. The displacement is parallel to the wave direction. So that for us, oh goodness, brain is not keeping up. Okay, so sound is longitudinal waves. Those air particles are being pushed in the same direction the wave is traveling. They're oscillating about their displacement point, but in the same direction the wave is traveling. Okay, periodic versus non-periodic wave speed and impedance.
Keep over impedance.
Okay, so impedance in general terms can be thought of as the resistance to flow or the resistance to the wave motion. And so the key things about impedance for our class so far have been that when there is a change in impedance, a reflection and transmission both occur. So changes in impedance cause reflections. So if you had a string that all of a sudden became thinner halfway through, at that juncture, there would be a reflection. Okay, for air traveling in a tube, when it's all of a sudden open at the end, that's a change in the way it's flowing, so there is a reflection. Yes, please.
If there is a reflection, like in those cases, what happens?
Okay, so the reflections are necessary for standing waves to be produced. Right? If it's no reflection, then you're never going to get a standing wave on a string or a standing wave in a tube that will actually generate enough sound to be heard. It also would be like an echo if it was far enough away. Right? And if the other end wasn't like attached, like if we could just go past, then it would just be an echo. If the end is attached, then it can set up that standing wave. Okay, good. Okay, speaking of reflections, that's the next one there. So echoes, standing waves, and then sound focusing, shadows, and dead spots are all the result of reflections of waves. Any of those you would like to talk about? Yes. Yes. Okay, so under reflections, the end conditions part. And sometimes it's called boundary conditions, especially if you aren't just dealing with a 1D thing like a string or two. Okay, the ones we've used in our class the most are fixed or free for strings or open or closed for tubes. And they determine how the wave bounces back. Don't know if you remember right at the very beginning, one of your first learning activities was the wave on the string where you could change that end condition, right? And if it was fixed, right, remember then that the wave bounced back one way, and if it was free, then it flipped over the other. Good. Any other questions about reflections? And then there's superposition. Which means that waves add. Any waves traveling through the same part of the medium, so whether it's a string or air or solid or whatever, will add. That's how they interfere with each other. And that can produce constructive or destructive interference and all of these other things. Yes, please. Yes. Okay, so masking is one of the examples of this. Okay. And this is when waves of different frequencies or sounds, but in there they're waves. They're anyway waves of different frequencies. excite parts of the basilar membrane. There are different resonances all along that, but then the basilar membrane motion is the sum of all of those movements. And so that means, for example, if you play low frequency type noise or something like that, okay, then it will tend to excite a relatively large part of the basilar membrane. So then if there are other sounds that are also exciting the basilar membrane, you know, maybe they only are exciting that much, you're not going to perceive them as much because the actual basilar membrane response would be this sum. But this sum is tied into the other. So it's that basilar membrane response that makes it so low frequencies mask high frequencies better than vice versa. Yes, please.
Can we go over localizing sounds and active noise?
Yes. Okay. So for localizing sounds, the principle is that for low frequencies, the head is relatively small compared to the wavelength of the sound. And so it is the phase difference between the two ears that is how we localize. It's how our brain learned to do it when we were little. Whereas for high frequency sound, the head is a relatively large object compared to to the wavelengths. And so that creates an amplitude or level difference between the ears. So in a way, the superposition here is actually happening in our brain. Right? You get the nerve signals from one ear, the nerve signals from the other ear, and in the brain, it's saying, oh, the phase is different. That means it's over here. Or the amplitude's different. So that probably means it's over here. Right? But it's still that idea of comparing, adding together these waves and figuring out the response. Yes. So phase means what part of the wave. So if this is one wave and the other wave was completely out of phase with it, then it would have peaks when the other one had troughs. If it was only up, so that would be half a wavelength out of phase. Okay, 180 degrees out of phase. But it could, right? It could be that the wave was not like that and it was only a little bit out of phase. Right? Again. So just the relative offset in time of the waves. Relative offset would indicate the phase difference. Okay. And if they are 180 degrees or completely out of phase, so 180 degrees is half a cycle. Because 360 would be all the way around the circle, right? 180 would be half a cycle. That would be completely out of phase. And if two waves are completely out of phase, what do? They destructively interfere. And lower the sound, right? Whereas if they are in phase, completely in phase, then you would have the constructive, the most constructive interference you could get. And other than that, it just depends. There's some level of interference, but you just have to figure it out by adding the waves.
Just remember, in fact, the phases are completely together.
Yes, in phases when they're completely together. So with that wave and you have one like that. They would be in phase. Now, they wouldn't have to have the same amplitude to be in phase. They just have to have their peaks and their troughs at the same times. Okay. Other questions? Yes.
So that kind of goes with like the first node is like that. because they completely replace each other.
Yes, so also that idea, yes, thank you for bringing that up. So that idea that mode one, all points are in phase, right? Meaning they're all moving up and same time and down at the same time. They all reach their highest point up at the same time, their lowest point. But for everything else, there is a phase different between different parts of the string. Yep. Good connection. Okay, anything else? All right, well, we